is shaped by the work of Yoshua and his lab to a large degree. And even if we don't think of Yoshua necessarily as an NLP researcher, I think many of the things which influenced NLP directly also were produced by Yoshua or his lab. So things like narrow language models back in 2003, or attention in Bartanov's paper. And for me personally, when I was starting as a green PhD student in, I think, 2003, that was actually narrow language model paper was one of the first two papers I think I read entering the field. So it's very personal relation to your work. I wouldn't hold it for longer, so without further ado, I pass it to you. I'm looking forward to your talk.
All right, thanks a lot, Ivan. Yeah, so I'm not really an NLP person, but I think a lot about language in relation to intelligence. And as you said, I thought a lot about the role of representations, distributed representations in natural language in the 2000s and the curse of dimensionality. And then, yeah, the machine translation work we did with attention, I think, has been something very exciting when it happened, and also had a lot of impact. But today I'm going to talk about sort of a third connection between my basic research in AI and language, and it has to do with inductive biases. So there is this paper that I mentioned here. It's called Inductive Biases for Deep Learning of Higher Level Cognition, which is an archive. It's submitted somewhere. Anil Goyal and I. It's a kind of position paper, if you want, or describing some of the work we've done and where we think there's an opportunity for deep learning to grow in the direction of the capabilities that humans have that I think are related to conscious processing and their ability to verbalize some of what's going on in their head. So that's the intro. All right. Now, a more kind of pure machine learning motivation for this has to do with the limitations both on the theory and the algorithms of our current methods in machine learning and NLP to deal with out of distribution generalization or transfer learning and so on. Our theory really tells us about what happens when the test data is from the same distribution as the training data. And in practice, our algorithms don't do such a great job out of distribution. So what does out of distribution mean? Of course, if you don't have any assumptions, then you can't say anything, and there's no reason why you would expect to generalize to a different distribution. But humans are very good at that. And so that's, I think, a very interesting source of inspiration. And there is, I think, a way to tackle, and I'm not the only one to talk about this, of course. There's a whole set of researchers in machine learning these days really interested in this, to tackle the notion of changes in distribution by thinking about how distributions change and thinking about, for example, the causal notions of interventions, and try to formalize how distributions can change that might be appropriate in many settings, and certainly looks like the kind of assumptions that humans may be exploiting and that we can see when they speak and verbalize knowledge. The other aspect of generalization out of distribution has to do with knowledge representation, because in order to generalize what we see, for example, in natural language is systematic generalization, where we can reuse pieces of knowledge that we already know, like the meaning of phrases and words and so on, in completely new configurations that have never been seen in the training data. But that only works if you have the right knowledge representation that decomposes knowledge in the right pieces, and of course figures out how to recombine them dynamically as needed. So as a motivation for looking at how humans do this type of generalization, think about the times when you're confronted with something really new that you can't deal with by just habitual behavior. And it forces you to think, forces you to reason, forces you to imagine, what could happen. And I think I have an example, like the driving example that I use in many of my talks. If you're driving on the usual path and you can be talking with someone else, you don't need to pay much attention to the road. You should probably, but in any case, that's what we do. Whereas if you're on a new place or there's construction or you're in a new city and traffic laws are different, you really have to consciously attend what's going on, and you're thinking about how to solve the problem, what to do, how to take decisions. It's a very different type of processing in your brain, and that has been studied by psychologists for a long time. I really recommend that book, Thinking Fast and Slow by Dan Kahneman. And so we have these two forms of cognition, system 1 and system 2. Roughly speaking, we're currently doing quite well with the first kind, with deep learning and machine learning in general. And it's about exploiting knowledge that we can learn through a lot of iterations, a lot of practice, but that knowledge is difficult to access consciously. So it's more like intuitive knowledge, implicit, whereas the system 2 type is knowledge you can communicate. So it's explicit, and also the way that we're using that knowledge is very different. It's very slow, sequential. If you write an algorithm, for example, it's exactly that kind of thing. If you plan consciously, if you reason, that's sort of system 2 operations going on. And the two things are not disjoint. One depends on the other. Mostly system 2 depends on system 1. System 1 can be quite happy by itself, but then it may not have the kind of generalization power that system 2 enables sometimes. And system 2 also has this systematic generalization capability of recombining things we know on the fly in order to understand, explain, predict, whatever. Okay, so another way to think about this is that of all the things we know that are at least our brain knows, because there may be a confusion here, there are basically two kinds. One is the verbalizable knowledge, and one is the not verbalizable knowledge, right? So, and probably the verbalizable part is the tip of the iceberg, which is why it's hard for humans to explain what they're doing. But today, and in the last few years, and probably the next few years, I'm thinking about that verbalizable knowledge and what advantage we could have by integrating those capabilities in neural nets. And the starting point for this research program is really to think of inductive biases, to think of priors, assumptions that somehow that are embedded in the verbalizable knowledge and our conscious processing abilities for that kind of knowledge. Because that's going to drive the kind of architectures that we need to incorporate those assumptions. And there may be a lot of different ways of incorporating those assumptions or priors, but I think it's important to be clear about what we are assuming of the world, at least for that part of that knowledge that I call verbalizable. And so now I'm going to go through a few of these inductive biases, often drawing inspiration from language. And maybe the one that got me started on this in the paper I wrote in 2017, it's already 4 years ago, called the consciousness prior, And really, the credit comes from Bernie Barr's global workspace theory of the late 90s, is the idea that the dependencies that we represent, the statistical dependencies or the causal dependencies that we represent to capture verbalizable knowledge are sparse, meaning that they involve very few variables at a time. So I have this example, like I have a sentence: if I drop the ball, it will fall on the ground. Now you notice that this is making a statement about the future, so we can make predictions. But interestingly, it involves very few random variables. There is the ball and its position, in the past and next. Maybe there's some context, like I'm holding the ball, and then I'm gonna do an action, which is drop it. And maybe there is some mechanism that captures like the physics of what happens when you drop something. So these are the actors, and you notice that there are very few little circles here, and that's unusual if you think about machine learning dealing with things like images, where you can't predict a pixel given 3 other pixels. It doesn't work very well. You need to kind of look at thousands of other pixels in the neighborhood. And maybe the whole image or something. So it seems to be very different from the kind of dependencies that we've been playing with in deep learning, like with sounds and images. When we get to language and we get to that kind of representation of knowledge, this sparsity of the dependencies seems to be a strong constraint. It's not a hard constraint. You can have 2, 3, 4, but we don't write sentences that have 50 different arguments. If we want to express something complicated, we use recursion. We basically combine many of these little statements in some way. So that's the first inductive bias. Another one is that the things we talk about in language have a strong connection to causal understanding of the world. So, of course, in the previous example, I was talking about the cause-effect relationship between dropping and the ball falling. But language also allows us to talk about counterfactuals. Like if I had dropped the ball, it would have fallen on the ground. So we can actually reason about the different possibilities of what has happened, what could have happened. And I changed now the little graph to incorporate the fact that this drop action cause can create an intervention that changes which mechanism is going to be used. Is it the normal inertial mechanism or the dropping mechanism? And so in general, I think the fact that language often refers to cause and effect is something that we should take into account when we model that kind of knowledge that is verbalizable, where the variables we want to, the entities that we want to manipulate play typically the role of cause, effect, agents, actions, interventions, and all that, which have a causality meaning. Now, in addition to talking about cause and effect, language also suggests a very strong assumption that the mechanisms, like the verbs, the interventions that are being described, are reusable, meaning there isn't like a separate verb for each object that the verb can apply. We can apply the dropping action to many different objects. So previously I was dropping a ball and now I'm dropping a phone, all right? Now, of course, this is obvious, but our current machine learning architectures, for example, in NLP transformers, don't really incorporate this kind of structure, the reusability of concepts. I mean, to some extent, but I think we need to revisit that to make it more aligned with this very flexible reusability that we see in language. And of course, that means we can do systematic generalization. If I change a sentence and I say, if I had dropped the zog, it would have fallen on the ground. Now we can do inference because we know about the kinds of things that can be dropped and that can fall on the ground. We know that zog probably refers to some kind of object, a physical object, right? In other words, this is telling us something about the entities now, not the mechanisms, and the relationship between the entities and the mechanisms, that there is some sort of type and attributes of these objects that make mechanisms applicable or not to different objects. And so objects have attributes that make it meaningful to apply different verbs, different mechanisms to these objects. So again, if you, from the linguistics perspective and cognitive science perspective, there's nothing new here. But the question I'm asking is, how do we take this kind of inductive bias into our neural net architectures so that we can achieve the sort of systematic generalization that humans enjoy? There's another inductive bias, which we can see in language, and we can see also in theories about causality. And that's the strong constraint or assumption that when there is an intervention, right? So an intervention is going to change the way that cause and effects are related to each other. In the extreme case, by setting the value of one of these attributes of one of these entities. So when there is an intervention, the assumption is that it's localized. It's, the typical intervention affects only one object directly, and of course, then there will be consequences. You can generalize that to have more than one for some reason, but the typical representation space that we use at the conscious level has that property that interventions refer act on a single object, but that means something like the entities that are manipulated and the kinds of interventions must have a very special property to achieve that. It's not something you would get in some other representation space. Okay. So many of the things I've talked about are related to very nice ideas coming from the causality research. And I strongly suggest in particular that you look at the Shopkoff et al. 2012 or the book that they wrote more recently, where they talk about independent causal mechanisms. And I think that's a very powerful idea that we have yet to integrate to its fullest potential in machine learning. And well, there are many ways to express this, but one way to think about it is that knowledge about how the world works is given by these mechanisms that I've been talking about. But of course, you could decompose your knowledge of the dynamics of the world in many different ways. So what is the right way? Well, the right way has the properties that we discussed in the previous slides. And but one way to express this that maybe I haven't emphasized is the idea that knowledge is decomposed, is factorized into these independent pieces. You can think of them like pieces of code. So we've already said the same piece of knowledge can be reused, but also two pieces of knowledge do not contain any redundancy. So that's the sense of independent here is independent in the sense of information theory, meaning that there is no mutual information between the pieces of code, which formally you could say, if I compress one piece and I compress the other separately, I get the same length as if I concatenate those two pieces and then compress. There's no gain by compressing them together. So there's not redundancy. If you think about how we write code, we try to achieve this, right? We try to factor our code so that the pieces are independent, meaning that if there is something that's redundant, we try to separate it into a separate function, right? And this has a consequence when we write code, but also a consequence when we think about knowledge representation and machine learning, which is that if there's a change somewhere, like an intervention, that requires modifying one of the mechanisms, that change is not going to impact other pieces. So when you write code, really what you want is that if you need to change one of the pieces, like its semantics, that's the only piece you need to change. If there are dependencies that suddenly make the code break because the way that the semantics of this piece of code really is not compatible anymore with the other pieces of code, then it's probably not a good way to write your code. And then the code analogy also tells us that we never completely succeed. And this is more like an objective that we would like to encourage our learner to optimize. Okay, now there is a kind of extension of the things I've said about the locality of interventions, which you find in language, that tells us something about the relationship between the representations of entities, events, and things like that in the world, on the one hand, and the representation of actions, of abstract actions. So I don't mean like one muscle doing one thing, but an abstract action like dropping. And the relationship is that is the one I already mentioned, that like these abstract actions, like people in reinforcement learning talk about temporally extended actions, options, hierarchical representations of actions. So these abstract actions have the property that they concern one object. Normally, you have verb object, right? And so so there's an important message here that you don't want to learn separately how to represent entities in the world, like objects and images, and how to represent actions, abstract actions in the world. The two should be learned together, because the actions are about controlling, typically, they are about controlling individual objects. And I wrote a paper a few years ago on kind of early insights about this idea, and we called it independently controllable factors. So, the idea was a way to disentangle abstractions, like from images and videos and stuff, if you can have an agent that can interact with their environment, is that the right abstractions have the right factors to explain the world, have the property that there exists also policies that are specialized to just modify that particular object or some attribute of it and not change the others. Of course, again, it's in the sense of an immediate causal effect, but there could be downstream causal effects. So then the picture that comes to emerge from a machine learning design point of view is we have the abstract level that can be verbalized, where we have these abstract entities and attributes that we can name. And we also have abstract actions that can be temporally extended, that touch individual entities. But then you also have the lower level, right? So we have videos, concrete and time synchronous sensory space on one hand, and also a concrete and time synchronous low level action space where individual low-level like robot actions are taking place. Okay, so let's go back to the causality aspect, what are the consequences of having the interventions be localized, which I've talked about already. But now, why is that interesting? So I have a little picture of a baby with dark glasses here, because think of what happens when you put on dark glasses. If you represent, things at the level of pixels, the joint distribution of pixels is now completely changed. Every pixel now has like a different lighting. And so accounting for that change at the level of pixels would be very painful. It's like you would almost have to relearn how to see. But if we have an abstract space of the kind, you can talk about, I put on my dark glasses. In that space, the change can be summarized as just one of the nodes, one of the random variables, having had an intervention. Basically, one bit was flipped that says I have, my dark glasses. So now, doing inference to understand that change, or trying to adapt your model to cope with that change with a little bit of data. Oh, suddenly everything is dark. Maybe I have my dark glasses. Becomes much easier, and you don't need as much data, right? So we wrote a paper in 2019, which was presented in 2020, where we try. It's called the meta transfer objective for learning to disentangle causal mechanisms, and the idea is, if you're looking to find the right representation space, as well as the causal structure, like is A causal B or B causal A, there's a clue that the right representations and the right causal models have the property that when there is an intervention, they recover from the intervention quickly. In other words, after intervention, the distribution has changed, and then your model is going to make wrong predictions, but you can adapt parameters. And if you have the right model, that adaptation is going to be very fast. Your learning curve is going to rise faster. And so we can take the speed of adaptation as an objective function to optimize our choice of representation and causal structure. And it works. And then there's been extensions of this idea by another paper in which I am, and also another in which I'm not, from colleagues at Mila with Simon Lacolle-Julien. Very nice paper presented at NeurIPS 2020 that formalizes a lot of these ideas and gives theoretical results. So let me say a few more words about these kinds of explorations. So we want to do causal inductions, like recover the causal structure from data that includes both what we call observational data, where there is no intervention and you just observe the data, sort of the world in its natural state, and also different environments where there has been an intervention. And a lot of our contribution has been, besides using the kind of objectives I mentioned, to deal with the case where you don't know what the intervention was. In classical causality work, typically they assume that the variables, the causal variables, are all known and observed, and when there's an intervention, you know what variable was modified. But if you think about a robot or a baby, they don't know ahead of time what the right space of variables is, and so for sure they don't know when there's an intervention which variable was intervened. Now, of course, with time, they come to have the ability to make inferences about what is it that happened, what was the variable that was modified by whom, and so on. And we can talk about it with language. So we worked on this question of the known intervention, and also using that inferred knowledge to really make this whole process work well by making the adaptation that is happening modify the right set of parameters. So if one of the mechanism has been bypassed by the intervention because we set the variable to some value, then it doesn't make any sense to try to adapt the parameters of that mechanism, which hasn't been used. It's not used anymore in the intervention world, in the new environment. And if you don't do that, then things don't work very well. But if you do, it really allows you to discover causal graphs. It's so let me skip this. We can learn both the causal structure, like where the edges should be in one direction, the other, or what, or not present, and also how to map like lower level data where everything is entangled into the space where there is a causal structure. Yes, so these are the same papers I've talked about. Another contribution of our work there, Rosemary Kay and collaborators, was how do we deal with the problem that if you have many causal variables, the number of possible graphs where you decide to put an edge or not, and whether it's directed in one direction or the other direction, is exponential in the size of the graph. And so we can't really enumerate all of the graphs. How do we learn the right causal structure in a computationally efficient way? And so the way that we've been doing this is by learning parameters or meta parameters actually for each edge that tell us, each directed edge tells whether that directed edge should be present or not, and then optimizing those meta parameters with respect to the speed of adaptation that I mentioned. Yeah, and it works. You can check those papers. Compared to at least existing methods, I think there's still a lot to do to improve. The conditional distributions in those papers are represented by neural nets. So each of these neural nets is going to predict one of the variables given potentially all of its parents, but then these probabilities we're learning about whether an edge should be present or not are going to be used to mask some of the inputs. So we're going to sample from those probabilities a graph, and that's going to allow some connections to exist and others not to exist. And so during training, it's like a sort of input dropout where you randomly allow only some random subset of the inputs to be used to predict each of the variables, but it's not a dropout like a uniform distribution, but it's that distribution over the edge structure is something that we learn as well. Now let's go back to architecture issues. So up to now, I've talked with causality on the what kind of objective function we could have. Another axis of this research is how do we take these inductive biases and change the design of our deep learning architectures. So yeah, attention, I don't need to tell you guys about attention, but attention really is maybe something we underestimate in how it is a deep transformation of how we think about neural nets. In particular, instead of operating on fixed size vectors, we can now operate on sets. Like the ordering between the elements doesn't matter anymore. It's there's potentially an implicit ordering in the keys that are used, but it's more powerful than that. It's basically operating on sets. Another interesting thing, if you're into cognitive science, is attention is a kind of internal action, right? So I can move my muscles, or I can somehow choose to think about something, to focus on one element in the input, or so these kinds of internal actions, they're like things our brain controls as well. And we should think about learning an attention policy in order to achieve whatever the system is supposed to achieve. All right, so about consciousness, there's a deep connection between conscious states and language, because indeed the way that we can know that somebody is conscious is they report what they're thinking about. And so that says something about the kind of representations, high-level representations that conscious processing manipulates. So language is a window in our high-level conscious processing, and especially system 2. Now, there are people who think that we can maybe do the sort of symbolic stuff on top of neural nets, and they're kind of independent, except that system 1, like ConvNets, might feed information to system 2. I don't think this is a good plan. I think that there are strong connections between the two, and I'll try to argue that. And one part of this that natural language people can appreciate is semantics, right? So I may manipulate the word dropping, but it's not so easy for me to completely explain what I mean. I can make a definition, but to have a full understanding of the word dropping, you really need to have your system 1 that kind of knows to recognize what it means to drop and predict what would happen at a level of detail that you can't easily verbalize. So system 2 is sort of manipulating entities whose semantics are really defined at the level of system 1. And that's why I think we should do a lot more research in a direction where the two systems are tied together, like in grounded language learning. Something we worked on with our Baby AI project. And I think this is really important for making progress on natural language understanding. In other words, I think there's a lot of knowledge about the world, as I said at the beginning, that is not verbalizable. And if we want to build machines which actually understand what humans mean, they will need to have access to that non-verbalizable knowledge as well. Hence the need for something like grounded language learning, where the data is not just texts. The data includes sensory level things and potentially low-level actions as well. Okay, so going back to attention, how we can use it. Of course, you know about transformers. That's just one way we can use attention, transformers and self-attention. But actually, it's a very rich tool, and we've been exploring how you can use attention to create modular representations of knowledge. So first paper on this a couple of years ago, called Recurrent Independent Mechanisms, was about a recurrent net architecture with a modular structure. So you have a bunch of recurrent nets. Inside each recurrent net, it's fully connected. But the connections between those recurrent nets are very sparse, and they're controlled by attention. So they can only exchange a few things at a time, and they exchange through matching queries and keys, essentially. Attention can also be used to decide which module is going to attend the current input and which part of the input is going to attend. So there's competition between those modules, again, inspired by the work in cognitive science and neuroscience about conscious processing. Yeah, and so there are lots of experiments that have been done, but actually many papers have followed up using similar ideas. One direction that works quite nicely and is even more directly connected to the global workspace theory of BARS and more recently Stan Dehen, a neuroscientist, is the way that the modules communicate with each other is going to be through a workspace. It's essentially the same workspace that the global workspace theory talks about. So it's a bottleneck. Think about your working memory. Maybe you only have 10 items in it. And there is a competition between those modules, which you can think of different parts of your brain, to write into the workspace. There's very few slots available, and many experts. So the modules which win the competition and put something in the workspace now are able indirectly through the workspace to broadcast that information. So everything in the workspace is going to be broadcast to everyone. So everybody can read from that workspace, but just a few at any time step are allowed to write into it. And workspace is also a set. So again, it's all attention to decide of all of these things. And interestingly, these kinds of architectures are particularly good in out-of-distribution generalization settings. For now, we've been mostly playing with toy architectures. I mean, toy problems like these multiple rooms and balls and navigation tasks and things like that. But we're scaling that up. Yeah, so this bottleneck idea you can apply to actually different architectures. You can apply it to transformers. You can create a sort of bottleneck. So for transformers are the column here. So you have the normal transformer architecture here, where every element at each stage, each layer can read from any other element at the previous stage. So our modification with the workspace introduces a bottleneck where only a few of the elements are allowed to write in the workspace. And now it's a kind of a small workspace. And then all the elements at the next stage can read from it. We have applied this to regular transformers, universal transformers, to RIMs and TIMs, which is yet another variation we explored that I won't have time to explain. Another extension of this, which I guess is going to be at ICLR 2021, separates the mechanisms from the entities. So in the normal recurrent net, you've got the activities of the neurons, and the weights of into those neurons are tied together. That makes it difficult to reuse the same mechanisms for different objects, for example. But at the conscious level, we seem to have that indirection ability. And so we explored architectures that do that. So one way to explain this is to look at the picture on the left here. You've got a bunch of entities, the object files, that's what they call it in CogSci. They're current, maybe they're extracted from visual input or things like that. And then you have the schemas or mechanisms that operate on these things, like their rules. And attention mechanism is now going to decide which rule, which schema, which mechanism is going to go with which object, and potentially multiple objects, because these rules can have multiple arguments. So the latest version of this, which we just submitted to ACML, is called Neural Production Systems. So it's yet another evolution on the same idea. Again, we have a separation between the mechanisms, the rules, and the entities that are sitting in slots in working memory. But now we only allow one rule at a time to be applied, which is another inductive bias that we get from CogSci at the high level. And there's only like one thing happening, one sentence, one phrase. And then we have this problem of selecting the arguments and the rule all together that are going to be winning the competition for the next change in the working memory. What's exciting about this architecture is that when we apply it on simple toy problems like parsing, reverse Polish notation, arithmetic expressions, or rotating MNIST images, it discovers the underlying mechanism. So in the case of reversible notation, in this case, there were only 3 operations, and there's going to be one module that discovers addition, one module that discovers multiplication, and so on. And same thing for the object rotations. There are only 4 things that can be done. No, sorry. Rotate, right, translate. Okay, yeah, 4 things that can be done and to an object, and it sees these sequences of images, and it discovers like the 4 underlying mechanisms, and it figures out which one is to be used at each point to explain the data. All right, I'm getting close to the end of my presentation, and I want to bring up something about how we process information at the high level. So remember, I mentioned that the actions, the applications of mechanisms or the interventions, they're not happening, at t+1, t+2, and so on. They are happening in a temporally extended way. So if you have time on the x-axis, and you have now these events that at the conscious level you pay attention to, these events, like this variable took this value or was changed in this way, are related to each other in a causal structure that has the, it's a sparse graph where the mechanisms take few arguments, and you only care about a few events and those events only talk about one entity or even one attribute of one entity, that something particular is happening to that variable. So this sort of graphical model, if you want, and the machinery to do inference and learning over them is something that we're working on, and I think is better suited to describing what we describe with language and manipulate with our thoughts consciously. Right. Another aspect of this is you can do inference to figure out what happened and learn, what were the mechanisms and how, what were the events that you want to care about. But you can also use these computational mechanisms to imagine things, to plan. Planning is something that, for now, in reinforcement learning, is done in a very brute force way that doesn't exploit the kinds of inductive biases I've been talking about. So this is another area that we're working on. I want, before closing, to highlight how this sort of research program I'm talking about is both inspired but quite different from the symbolic AI program of the previous century. Basically, we want to have the best of both worlds, right? We want systematic generalization, factorizing knowledge in small exchangeable pieces, being able to manipulate variables, instances, and some kind of interaction. And attention is a key ingredient for all of these things. And all of these things are present in kind of classical AI. But we want to keep the things that work well with deep learning. We want to be able to do this very efficient large-scale learning. We want to ground those symbols and those high-level entities into system 1 implicit knowledge. We want to continue represent these entities with distributed representations because of the powerful regionalization that comes with it. Also, we want to use system 1, like typical neural nets and maybe generative models, to help with the search problem. Like in AI, one of the classical symbolic AI, one of the big problems is how do you search? That you have like an exponential growth in the number of paths and combinations of rules that you could entertain. If you look at how humans do it, at least at the conscious level, it looks like we're not scanning through millions of possible paths. We just have one or two that comes to our mind almost for free. So the mechanism that does that is subconscious, and it's system 1, which means we can probably learn to generate good candidates for reasoning. And of course, we don't want to lose all the probabilistic aspects that we have mastered in modern machine learning to deal with uncertainty. My list of open questions, that would take time. Let's see quickly some of the things that I think need a lot more work. How do we jointly learn the encoder, like the map? This is the central thing of deep learning. How do we learn representations? That's the encoder. But we want to learn it at the same time as the causal graphs and the mechanisms. And we only have baby steps in this direction for now. What happens when some of these abstract variables are it's not just that they're not observed, that they can't be inferred perfectly. There's ambiguity in their values. We haven't done anything in that direction. How do we tie the abstract entity space, the variables, and the abstract action space that I mentioned? We haven't done anything there except saying this is something that should be done. There's a lot of questions about how to do inference and combine inference with there are different kinds of inferences, for example, in machine learning that I think makes sense to think about here, like the very fast inference, like you have in a VAE, it's just one feed-forward pass, and you have slow inference, like in the Boltzmann machine, iterative inference, and human brains seem to do both. There are lots of interesting questions about memory, and I mentioned how to search efficiently, how to do credit assignment through long time spans with this asynchronous causal graph I mentioned. All right, thanks very much. I'd be happy to answer questions.
Thank you very much, Yoshua. Maybe I'll start off. So I think you hinted at some similarities between language sparsity and similarity between, say, causal graphs, right? Definition of decomposition. But I didn't see you making this connection more explicit. Do you think that language can in some way guide the search for plausible causal structures, or you should use only statistical information theoretic mechanisms for doing that? Mm-hmm.
No. Okay, so language could be useful in many ways. So first of all, I've already kind of insisted in my presentation that language can be an inspiration for inductive biases. In other words, how we design these architectures. But language data can also, when I talked about grounded language learning, can also help to provide clues about what are the right high-level entities. Basically, they correspond almost one-to-one to words. I mean, not exactly, but something very close. So the mapping should be very simple. And so I'm pretty, I have a strong intuition that if babies didn't hear any language, it's not just that they wouldn't be able to speak, but their understanding of the world might be much worse. Not just because of the explicit knowledge that is given in language, like, oh, don't get close to lions or something, but also to discover what are the right abstractions. Yeah, so now how to connect all these things together? There's like a lot of work in front of us, and I wish more people. I think I see more and more people working in these questions, but I think we need more. And especially, I think it would be great to have more people on the NLP side involved in this.
No, it's interesting to see that we can be not only users of technology, but language data, language model can actually affect higher.
Right.
So I think Andre Martins has a question. Andre, do you want to just turn on your camera and microphone?
Yeah. Sure. Yeah. So my question is to do with the, in several places in your talk, you talked about the sparsity assumption, which seems to pop up in different places, right?
Yes.
So there is the sparse dependency assumption in system 2, the sparsity that we have when you do competitive learning for REMS, the sparsity in localized interventions.
Yes.
So what else can these sparsity biases besides improving generalization? Can you also use it to get smaller models by reusing concepts, as you were pointing out in the beginning, and having to memorize?
Sure. I mean, that you would expect that if you have the right causal space, the knowledge representation is going to be more compact. In fact, it's almost like a side effect of the independent mechanisms assumption, because otherwise, if you had redundancy, then you haven't factored properly the knowledge. So yeah, and sparsity, is also important for systematic generalization, right? Because it makes it easy to recombine pieces when you only recombine a few pieces at a time. So if you have to choose from a large number of elements from a large set, the search problem is very hard. But if you only have 10 things in your working memory, then and maybe you only typically care about picking 3 for some inference about a dependency that links them that you care about, that makes the search for like choose those 3 much easier than if we didn't have the sparsity constraint.
Yeah. Thank you.
James Henderson, I think you had a question, right?
Yeah. I really think this is a really important research program. Just a quibble that, and it's also very relevant to NLP, but in NLP, we're often concerned about the structure. So we have multiple things that we're talking about, but we're worried about their syntactic structure or semantic structure. And one of the things you said was that an action typically applies to a single object, which I don't see how you can get structure. It seems like you need, as you just alluded to in your answer to the previous question, sometimes you need to pay attention to more than one thing.
Oh, yeah.
And maybe that's crucial to human intelligence.
No, so you typically have more than one argument to the verb, right? But there's one that is kind of special, that is the object. It's the thing that you're changing, say. That's what I mean.
Okay, so that might be why we have subjects. Subjects have a special status in language. Maybe that's why. That's
right. And subjects, if you think in the causal way, subjects, verbs, and objects, which are like the heart of syntax, they have a special semantic, causal meaning, a special role that fits perfectly with the causal understanding of knowledge. So it's not just like a name or a role in a parse tree or something. It's something that has to do with how reality gets to be modified and understood by human beings who do things in the world.
Well, there could be entities at lots of different levels that actually reuse the same mechanism. And you're talking about the conscious level, but I mean, the same mechanisms could be applied.
I mean, obviously, there are lots of things that are happening at the unconscious level that also involve these entities, right? Absolutely.
I think these are all very interesting discussions, but maybe we can continue them in a panel format, because I think this time to switch to the panel, unless I'm mistaken. No, I don't think so. So then I hand